Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, where we talk about nuclear binding energy, or the force that forces the protons to be near each other. Because if you know anything about protons, they have the same charge and they want to repel. So there has to be something else that's holding it together, and that something else is the nuclear binding energy. So the way that you solve this problem is by trying to figure out the mass of the nucleus versus the mass of the individual parts, okay? So in this problem, we have kind of read the prompt, and we discover that the nitrogen-14 nucleus has a mass of 13.999234 AMUs. And as you can see, I am taking this out a lot of digits because the mass difference is going to be really, really tiny. So we have to take our decimal points out really, really far. Well, a nitrogen-14 nucleus consists of 7 protons and 7 neutrons. So we're going to try to take this nucleus and kind of break it up, because what nuclear binding energy is, it's the amount of energy required to separate the nucleus into its individual parts. And that's basically by removing the nuclear force or the binding energy that's holding the nucleus together. So our nitrogen-14, we're going to separate it into 7 protons and 7 neutrons. And the numbers for protons are 1 and 1, neutrons are 1 and 0. And what we need to do is we need to look up the mass of protons and neutrons. And we can no longer use relative mass. We need to come over here and use the exact mass of protons and the exact mass of the neutrons. So a proton has an exact mass of 1.00728. So we're going to figure out, well, how much does 7 of those 1.00728 AMUs is going to weigh? Okay, so these are my 7 protons, okay? And I'm going to add 7 neutrons to it as well. The neutrons are 1.00866, 1.00866 AMUs, okay? So this side is actually going to weigh different than this side, and that should kind of blow your mind, because everything that we've done in chemistry up to this point has been this like law of conservation of mass, where the one side has to equal the other side. Well, this should make you uneasy, okay? And we are going to kind of like, I guess, rectify the situation at the end, okay, and explain like what's going on. So let's go ahead and add up the 7 protons and 7 neutrons together. We get this mass of 14.11158 AMUs, okay? So there's a difference here, okay? We're starting out at 13.99, okay, and its individual parts weighs 14.11. Seems kind of crazy, okay? So what we're going to do is we're going to calculate the difference in mass, and we're going to call that the mass defect, okay? That's an actual vocabulary word in this unit, okay? And whenever you find the change in mass of anything, it's always going to be the final minus the initial. So I'm going to take 14.11158 and subtract 13.999234 to get this answer, okay? So maybe I'll just write that down for you. So 14.11158 minus the initial, which is 13.999234, is going to be equal to 0.112346, and this is going to be in AMUs, okay? So there's this difference in mass that we need to account for. We need to rectify it. We need to kind of like take care of it, okay? And this is where Einstein's famous equation of E equals mc squared is going to come into play. The c is going to be the speed of light, okay, which we know is going to be 2.998 times 10 to the 8th, and that's meters per second, and that's going to be squared, okay? And the only way we can get a joule, and this is kind of like some unit analysis, is if you know that a joule is actually equal to a kilogram times meter squared over second squared. Now I'm going to have the meter squared over second squared. I'm going to have this part, but this mass can't be AMUs. The mass has to be in the unit of kilograms. So I got to take this number, which is 0.112346 AMUs, and I need to get it into kilograms in order to place it in the E equals mc squared equation from Einstein. So let's go ahead and convert AMUs into grams first, and then grams into kilograms. And I have these conversion factors over here on the side if you forgot them, okay? So the conversion factor between grams and AMUs is Avogadro's number, 6.022 times 10 to the 23rd. That's a lot of AMUs to make up 1 gram. So this AMU unit is really, really small because it takes so many of them to make up a single gram. And then I really hope that you know that there's 1,000 grams in 1 kilogram at this portion of the course. So we plug this in, okay, we do the calculation, and we find out that this mass comes out to approximately 1.866-ish, okay? We're going to try to keep all the digits in our calculator, times 10 to the negative 28 kilograms. Well, this is the mass that I'm going to plug in here because it has to be in kilograms. So the energy, the binding energy that holds the nucleus together is this mass times the speed of light squared. So let's go ahead and put that in there. 1.866 times 10 to the negative 28 kilograms. Of course, I'm trying to keep all these digits in my calculator when I work it, okay? But when I work it out, I find out I get a final energy of 1.677 times 10 to the negative 11 joules. Now, I want to let you guys know that is for one single isotope of nitrogen-14. So over here, I'm going to put it as a per isotope. So to break up an individual isotope of nitrogen-14, it's going to cost me 1.677 times 10 to the negative 11 joules in order to break it up into 7 protons and 7 neutrons. Now, a lot of questions aren't going to ask you a per isotope basis. They might ask you a couple questions. One of the questions they could ask is, hey, can you put that on a per mole basis, okay? Well, if you're going to put it on a per mole basis, you're going to have to multiply by Avogadro's number, which is 6.022 times 10 to the 23rd. So if I take this number and multiply by 6.022 times 10 to the 23rd, I will find out that I get 1.01 times 10 to the 13th power joules, but now we're talking about per mole. Okay, so that's for a full mole of nitrogen isotopes. Okay, so that's why the number is so much larger than the per isotope number. The other thing that they could do, which is actually it's fairly common and it might surprise you, is they might ask you to put it on a per nucleon basis. And you might say, well, what in the heck is a nucleon? Okay, a nucleon is simply, okay, a subatomic particle that's in the nucleus. So they're really just the protons and neutrons. And how many protons and neutrons do we have in the nucleus? Well, if we have 7 protons and 7 neutrons, we have a total of 14 nucleons that are inside the nucleus. 7 of them being protons and the other 7 being neutrons. So really a nucleon is just a subatomic particle inside the nucleus. So all I'm going to do is take this number and I'm going to divide it by 14 because there's 14 nucleons inside the nucleus. So 1.677 times 10 to the negative 11 divided by 14, okay, is going to give me the number of 1.198 times 10 to the negative 12, and that's going to be joules for every nucleon. Okay, so joule per nucleon is this number. So when we're doing binding energy, there's 3 answers that the prompt could be asking you, and you need to answer it appropriately. Is it asking for a per isotope, a per nucleon, or per mole basis? Okay. Now the next video is going to have a sample problem to see if you can do this again all on your own. So go ahead and go to that video, okay, hit pause at the beginning, work the problem out, see if you can do it, okay, and I'll have the answer at the end. But that you can find all that in the next video. But if this helped you learn about nuclear binding energy, please give it a like and subscribe. Share it and share it with people. Leaving a comment actually really helps the algorithm push this out to other students that might be interested in learning chemistry.